To create rock star sounds, guitar players mix and match modular pedals to combine effects like distortion, reverb, and delay. When he hits that first power chord, the signal travels from the guitar through the pedal signal chain to the amp and then blasts it out of the speakers, bringing the cheering crowd to their feet. Here to talk about a similar modular signal chain system is James Staley, the Power Systems Engineering Manager at Analog Devices. James is going to show us how Analog Devices' signal chain power platform can turn us all into electrical engineering rock stars. James, welcome to Tech Chats. So to get started, James, can you help us define what we mean by signal chain in this context? What is it? How is it used? Where is it used?
So when we talk about signal chains, we're talking about basically everything that couples the real world that's measuring temperature, vibration, sound, pressure, some kind of transducer or sensor, and all the electronics in between that and the digital domain, either the output of an analog to digital converter or straight into some ASIC that has it built in before it goes into an FPGA for further processing. So you're typically looking at some kind of front-end amplification and some filtering, and then the converter. Those are kind of the core elements of the signal chain.
So lots of applications that could fall under, right?
Oh, absolutely. Everything from, precision instrumentation to automated testing equipment to machine health and monitoring, radar returns. I mean, there's everything in the industrial, sometimes consumer space, but mostly industrial and mil-aero segments that these signal chains are quite common in. Their bandwidth, their signals of interest might change, might be different, but a lot of it is kind of looks the same on paper, I should say.
Right, but very few people in our audience are going to look at this and say, not really applicable to my space, right?
Right, but you find the signal chain concept in a lot of equipment and processes, and also, I should say, designs and applications. Anywhere there's an amplifier, some kind of an ADC, that's a signal chain. That's the kind of the prototypical form of a signal chain. If you have something that's being measured in the real world that then goes into some kind of processor, that requires a signal chain.
So basically, you guys looked at that situation that applies in so many different places, and you decided that you at Analog Devices were going to make a really modularized hardware evaluation platform, right? That's what we're going to talk about today.
Yes. So the reason why we came up with this approach, or I should step back and say is a basic introduction to signal chain power, is what we found first in the applications and later in the systems group, is we found that there were some common obstacles to getting the performance that people needed. Oftentimes it was for noise reasons. And we found ourselves asking, how good is good enough? And a lot of times we couldn't get an answer, or someone would say, well, I used LDOs, that's linear regulator, and I still see spurs in my FFTs. Now what do I do? Sometimes it had more to do with the converter performance in general. People would ask, why can't I just use LDOs? Won't that solve everything? Or application-specific questions like, well, which topology should I pick if I have a battery, if I have 12 volts in, or if I have 24 or 48, even higher volts in? Or people would say, look at parts and say, well, why can't I get 10 milliamps out of this, quote, 50 milliamp boost? Questions like that occurred. And so we were trying to address that.
So this slide is kind of like a little guide to some signal chain designers' anxieties. Yes.
Yes.
It's of you to put it all in one place.
So our group decided that we should try a new approach to power development, and that was to create a hardware evaluation platform that was modular. So what the signal chain power, or what we call SCP for short, system is it's a series of small modular blocks for signal chains. With that, you can build up a complete solution by just kind of plugging and playing and replacing blocks as you need to. And it comes with full engineering collateral, all of the schematics, layouts, bills of material. We have 36 boards currently in the program, more on the way. Those include the power boards, interconnect boards. We also have some additional support like a custom LCR filter board, and some additional boards are possible if you want to roll your own using the SCP board format standard that we've created.
So you can actually do some custom boards is what you're saying?
Yes, absolutely.
Oh. Well, let me ask you this. So, as you've talked about in some other collateral that you've put together for SCP in the past, I thought that was really interesting that you actually said that part of the appeal of the platform is that you can have signal chain system power designs without necessarily real power design expertise. Is that something that you could expand upon? And, do you credit that to the modular nature of the platform? Where does that come from?
Yes. So the whole point of the SCP program was we were trying to simplify the design possible in cases even where there wasn't necessarily some power expertise available on the team. So the way that we tried to reduce the design cycle time for signal chain was to take all of the best know about power that we have on our team and pick the best part out of, thousands of parts that Analog Devices has, and pick the parts that were most suited for powering signal chains, and then to leverage the SCP configurator software tool to make that design faster and easier. And when you make hardware evaluation and validation easier, it means less time spent in the lab wiring up boards or, trying to modify demo boards into some kind of custom kludge. And another thing that happens is when you have a bunch of demo boards, they're all wired together, it's pretty large. So if you're trying to take that huge array and couple it into your target processor or signal chain board, that sometimes means lots of wiring going all over the place. And the other thing is with the small form factor and them being all in the same program, you can swap out boards. You can change certain design elements and see if your noise improves or see if your power consumption or efficiency improves.
Right.
Those are all things that simplify the design cycle.
Well, and this might be a weird question, but less wiring and lab effort. Do you think that there are some engineers out there that are going to be just sort of like, "Aw," they really like that part of it? There's some sort of artisticness to the suffering of wiring these things together in the old fashioned way.
Yeah, there might be some of that, but what we've found is that oftentimes, joy of tinkering aside, most people who are trying to design their power for their signal chain, power is the thing that they're least technically proficient in. It's almost invariably the very last thing everyone saves for the very end when all the, I should say, ugly surprises pop up.
Right.
And so usually when they get to that crunch, they just want it done, and especially they want it done right.
Mm-hmm.
And that's where SCP can really save time. We say with SCP, you can have faster system development with less delays. A couple ways that's made possible is you don't have to wait for the rest of the hardware team. You can have a very fast system validation with the SCP program, and you can verify the performance before it actually goes to layout. Since all of these boards are using the best known layout for every particular chip, once you plug them all together as a complete system and see them working, you kind of know what your performance benchmarks are going to be. You don't have to wait till it goes through CAD and then comes back and then start validating your power. You can validate your power before it ever goes to layout because each board already has the best layout for that part recommended.
Mm-hmm.
So you don't have to let CAD be the bottleneck. And if you do find errors, you can change your designs more quickly, right? All it involves is swapping out a board.
Mm-hmm.
You don't have to wait for an entire respin of all the power and all the other components on a big giant custom system board. And if you do go to a planned board revision, you can explore other ideas before you actually do that.
I kind of like that this slide functions as the anxieties of a system designer part two
Yeah.
a little bit. And before we actually move on, just a little bit of context for that CAD is a bottleneck concept. A lot of the engineers in our audience, they got into their engineering career recently. We've got a lot of young engineers that are, learning the ropes, or they're very used to tools like CAD tools. And maybe they're looking at this with a little bit of a different context in regards to, like how could CAD possibly be the bottleneck? Can you help us understand a little bit about like why this type of hardware like simulation is beneficial? Where is it cost effective? And in the process, maybe you can give them a little bit of advice about when they're talking to their engineering manager. How do you help them basically pitch this as a solution that they want to be able to use?
Well, that kind of segues just nicely into my next and final point here, was that you don't want to reinvent the wheel. The SCP program already has all the proven design and layout strategies, so you can migrate all that collateral directly into your project. But to answer your question directly about the CAD program, the SCP configurator software is free. So that's a really easy pitch to any engineering manager.
It's an easy sell.
Right. Yeah. And that tool is designed to take an input voltage range and all your specific output voltages and currents you're pulling straight from your data sheets. And it takes all the best know we have about how to design topologies, and it directly picks the parts for you. So what I meant when I said CAD can be a bottleneck was specifically the layout. And with switching regulators, there's a lot of kind of voodoo that goes into getting the layout just right. And it takes years of switcher specific knowledge, intuition and expertise often to get switching layouts just right so that they're not either oscillating or radiating noise all over the place. And if you stick with the collateral that's available for all of these boards, you won't get into any problems because we've already given you the best layout possible for that part.
Right. That makes a lot of sense. And I guess this is a good time to ask that question about, obviously you're touching on a lot of pain points that engineers have been sort of wrestling with for years. That's why, these slides are such good little, basically lists of all the anxieties of what these engineers are up against in a day-to-day basis. But obviously there have been some solutions in the past that people have been using. Can you tell us a little bit about like what's been out there and why you guys decided to basically take on the next iteration and address whatever problems were left over from those solutions?
Well, that's a good question. And there are, I'm sure, plenty of engineers who would ask, are there power demo boards already available? And the answer is yes, but we've kind of touched on that most demo boards are meant to highlight all the functionality of the parts. They're there to advertise and really show you everything that's great about that part. So they're large, they have lots of turrets and jumpers and settings, and oftentimes they'll have multiple topologies, and it makes the solution size a lot larger. So now you have a board that's 4 inches by 6 inches, with all kinds of confusing stuff around the edge of it, and all kind of hooks so that you can really exercise that part and all its capabilities. And SEP is not a replacement for evaluation boards. We developed the signal chain power platform to evaluate and develop entire systems, not to evaluate parts. So the SEP part selection is limited to the parts we thought were best for those signal chains. And the demo boards are typically applications flexible, but the SEP boards are not. They're meant to be compact so that you can take an entire system, 5, 6, 7, 8, sometimes 12 parts, and have them all condensed down when they're plugged together in the size of a sheet of paper.
That is pretty impressive.
Yeah. And the flip side is that, SCP is not really geared towards higher current applications. They plug together with standard header pins that are all rated about 2 amps max.
And these building blocks are pretty no frills, right? Like they're designed to, just be as modular and simple as possible so they apply to the most situations possible.
So while there are existing demo boards out there, nobody, at least to my knowledge, has really come up with the idea of stripping out all the stuff that makes demo boards
right,
and focused on letting them all plug together from a system-centric point of view.
Yeah, that's an interesting concept. I think that there's a lot of dominance for those evaluation boards, those demo boards in the market. So this is kind of a different paradigm, I guess you could say, right?
Yeah.
Moving on, when you're talking about this SEP portfolio, there are many options. You guys sort of, what did that process look like? Did you guys sit down and kind of list out all the possible pieces that you would need to include and turn it into a sort of mix and match formula? How did you guys approach that?
So the way we approached this was my director and we sat down with, at the time there were 5 different power groups at Analog, and we sat down with the design managers and we said, when it comes to powering signal chains, typically low current, high noise requirements, or I should say, high PSRR, very low noise is what you're trying to shoot for. What parts would you recommend? And these were people who had spent, 10, 15, 20, sometimes 25 years managing groups that were designing all kinds of different switchers and LDOs. And they each gave us sort of their top 5, top 6 parts that they thought were most beneficial for that market segment. So we started with those parts. And then as some newer parts came to market, we added those into the portfolio. So what you see here in the list of switchers, they are basically, as far as we could tell at the time, the best in class for these particular signal chain applications. There's a lot of older bipolar parts that typically switch a little slower. They throw off a little less noise. And what we did was we took all of the bucks are available both in a positive buck, and we came up with a special layout for easily with just moving a couple small resistor jumpers, taking that from a positive buck to an inverting buck boost topology such that you can have either positive or negative voltage output with them. And we include some boost and some SEPIC, so all of the major topologies here in the switchers are included.
Yeah, and that's actually before, we talk about the next sort of group here. Can you shed a little bit of light on the differences between these sort of standard versus micro power buck converters and why an engineer might choose one over the other?
Yeah, so we try to come up with a wider range of parts while keeping the portfolio size small. And some of these bucks will have very high switch voltages allowable. So if you're coming in from 48 volts down to, let's say, 5 volts or 12 volts, you can do that with those parts. Additionally, if you're trying to go from, let's say, a high positive voltage to a lower intermediate inverted output voltage, a 60 volt switch is great because the total switch stress in the inverting buck boost is, the absolute magnitude of V in plus negative V out. So the 60 volt bucks are included. The micro power parts, that typically denotes a switch current rating of maybe 10 to a couple hundred milliamps, as opposed to high current bucks, which are, in the tens or 50 amps of switch size. Those parts aren't really applicable in this particular segment, signal chain power. So for the most part, you'll see micro power parts. That's just how most signal chains are typically powered. They don't consume a whole lot of power.
Right. Okay. So this is we're just kind of putting ourselves in the shoes of that engineer who's making these decisions, and these are all sorts of everything that you just explained. That's going to be part of that decision making process that you expect these people using this platform to kind of go through.
Right. And the great thing about the tool is it completely removes any guesswork. If you specify an input range and an output voltage and current range, it will pick. Our team thought long and hard about how to design the tool, and we have a unique proprietary algorithm that kind of looks at things from a peak current point of view and makes decisions about what the best part is. So it will calculate what the peak switch is, and it'll make a determination about what the best part to use is based on that as part of the selection criteria.
Awesome. Yeah. So you just talked a bit about these switchers. I know the next thing that we were going to be talking about was those low dropout linear regulators. We move on to those ones, and you can sort of walk us through what we see there as well.
Yeah, so the SAP approach when it comes to linear regulators, earlier I had mentioned that a lot of times when we were trying to design power for signal chains, we would ask people, well, what kind of noise performance do you need? And they couldn't give us an answer. And so, it's really hard to pick apart when someone can't tell you quantitatively what kind of noise performance they need. They tend to answer you more in qualitative terms. Well, it has to be low noise,
Right.
or it has to be very low noise. But what does that mean? So what we did was we found 3 different sets of complementary LDOs, the ADP 7142 and 7182, the LT 1962 and 64, and the LT 3045-1 and 3094. And what that represents is kind of, solid, low noise, very low noise, and extremely low noise, ultra high PSRR LDOs. So kind of a low, middle, high approach.
So you kind of decoded their non-answers for them.
Right. So what that means is because these are modular, we recommend, hey, start with a 7142, 7182, and plug it together, change the voltage, run some FFTs. If you see spurs you don't like, then go to the 1962, 1964. If you still see spurs you don't like, then go to the 3045-1 and 3094. And if that doesn't work, you you have some really interesting application requirements.
You should give us a call and we'll talk about it.
Yeah. And then for good measure, we found in many cases people just need very small, there aren't any high noise requirements, or I should say low noise requirements. They just need a voltage change. And so for that, we included the ADP 150, which is a series of very low cost LDOs in fixed voltage ranges. And they can throw those down all over the design as necessary for logic voltage rails or some auxiliary rail to bias up LEDs, whatever they need. It just costs a couple pennies.
And we do have a couple of questions about that coming up as well. But before we get there, we've got Another one that's a really interesting one is the interconnect hardware. Can we talk a little bit about how you guys chose to put this hardware together? Obviously, anytime you have these connectors, there's a possibility of parasitics that you don't want to end up in the finished product, but can change, the way that you think about your system. How did you guys accommodate that in the development cycle? How did you guys approach that when you were designing this platform?
So that's an interesting question. My director sent me to my cube and basically said, "Don't leave until you come up with a
Oh
really
no.
clever way of making all these demo boards pluggable together." Yeah, was
No
was
pressure.
kind of the mission. Yeah, no pressure. Uh, so I went to my whiteboard and started doodling, and I actually still have a photo of my original concept sketch, and we
Nice.
put that on our internal website for a long time.
Oh, cool.
But it's interesting you talk about the parasitics, and we have a lot of interconnect hardware to make the SAP program work, and it's kind of both a backbone and the glue that hold everything together. So we have a 1 to 2 and 1 to 5 breakout board, and that allows you to branch out from a single voltage into parallel streams of voltage. And then we have a 5 to 1 integration board that kind of brings all those rails back together.
Mm-hmm.
And once we had them, we thought about the parasitics involved and also what we wanted to accomplish with those boards, since it was a large chunk of real estate in terms of PCB. So we threw on features like you can add filtering.
Mm-hmm.
There are some sense resistors there with Kelvin connections, so you can measure individual branch currents if you want. We put some LED indicators there. They're bidirectional LED, so if it's red, it's positive. If it's green, it's negative, or vice versa, I should say. And we have some input boards and output boards, and those basically will couple the entire platform to the benchtop power supplies and active loads, meters, things like that. We have a through board that acts as a spacer element. If you have a switcher and an LDO on the rail above it, and then you just have a switcher or just an LDO below it, you kind of have to make up for that empty space since the row above has two. That's what the through board is. We also have a custom nth order RCL filter board, so you can design. If in the final design you don't want to have an LDO, or if you have an LDO and need additional filtering for a specific band of frequencies, you can plan on that and actually test it in before you can validate that custom filter by using that board. And the nice thing about those boards is it actually kind of simulates some of the real world parasitics that you're going to have in your final board.
Right.
There's no way you can have a custom board without at least a few inches of PCB trace. So we have found that you actually get some filtering for free. For example, on the through board, it actually tends to mitigate some of the high frequency response in terms of how it rolls off. And that does a good job kind of approximating what at least a few inches of PCB trace will do. So in some sense, those parasitics actually work with you instead of against you.
Interesting. So that's where that simulation sort of piece of the puzzle comes in.
Actually, it's not simulation. It's real hardware. That's the great thing. Sometimes people want to do their entire designs in SPICE, and that's a great tool. The problem is it's really hard to simulate parasitics.
Mm-hmm.
This board actually gives you, depending on how large your array is, some real parasitics you can measure.
That's awesome. And just a little point of interest there from the engineering side, from our desk here. Just a quick question. When you're talking about that 4-point Kelvin connection measurement of the sense resistor,
Mm-hmm.
can you tell us what that's actually measuring? Is that measuring the current through the power supply? What's that actually taking a look at?
Yeah, so the boards come standard with basically low impedance jumper resistors. It's just a chunk of metal over that. But if you want, you can replace that with a precision sense resistor. And because it's a Kelvin connection, you're getting a third and fourth wire that are basically going right to the terminal of the resistor. So you can very accurately measure the current flowing through that point without including some extra either resistance of the copper along the pad or stray currents flowing through there. So it just gives you a very precise way of measuring the current through any individual chain if you're interested in measuring those.
Right, because those, as you mentioned, there are several things that you can kind of add on ad hoc as you require them. So that includes, measuring noise. That can be measuring like power throughput in general. Yeah.
Right. And
Awesome.
so, for example, the 5 to 1 board, the integration board, that has a special connector on the end of it, so you can create your own custom pigtail to then marry up to your target device. It has dual SMA ports if you're interested in making very accurate noise measurements, like with a LISN setup. And you can pull the power off of one SMA if you're in a 50 ohm environment for high speed signal chains, and then take a measurement off the other one. So we thought of a lot of different options. Since we have the circuit board, let's loaded up with goodies.
Right. Yeah, I feel like to some extent, being a fly on the wall as you guys came up with these concepts would have been really interesting for some of these engineers. So let's talk about implementation, actually getting your hands on the platform. So perhaps one way to look at it is that you guys have put together a system that has a lot of freedom. There's a lot of different things you can do with this. And I suppose one way to look at it is that if you don't go in with a structured plan, maybe that much freedom can go wrong if you don't have the steps in front of you. Maybe it's the with great power comes great responsibility speech of how you're going to end up using the actual platform. Like, so can we step back into the shoes of the engineer who is considering reaching for this? When they sit down and they start working with it, what do you expect that process to look like?
Yeah, so we've tried to streamline the process of how to use SAP resources to the extent possible. And if it's can be broken down into a three-step process, it sounds something like this. Utilize the website for content. If you go to Mouser.com, you can look at all the boards that are available and you can get the configurator tool. So once you get your software, you download it, install it, you can do a simple design and it will pick the parts for that system to use. It'll give you a list that you can order from of all the interconnect boards that you'll need. You order the boards from Mouser, they arrive. Step 2 would be to prep the hardware. So while the SAP configurator or software tool creates the design, all the collateral that you can also download from Mouser.com is the individual demo manuals and schematics and bills of material. Those are things that you'll need later on. So you'll follow the applications guides to choose for example, the resistors for the output voltage you need to program, all of the most common voltages that you might need, sometimes in 1 volt increments. They're in a chart in those application manuals. So you just go to the lab, change the resistors based on what the application manual said to, plug the boards together, power and test them individually, then plug them up as a system and use them in your actual application. And then if that doesn't work or if it doesn't give you the performance you need, you can try alternate parts. You can go back to Mouser, order more boards, or if you're smart, the configurator tool also gives you a list of alternate recommended parts to try. So you can order those at the same time as you get your first batch. And then if you do want to change some things up, you already have them in your back pocket.
All right. So putting ourselves in the shoes of that person who's going through this process, as you just described it, can you ballpark for us a little bit about how much time do you expect this process to take? And on top of that as well, can you tell us at all about, what's the order of magnitude in terms of budget that people should be expecting? Because obviously there's a lot, you're getting a lot of use out of the multiple pieces, but are we talking is this $1,000 budget that we're dealing with, a $10,000 budget? What should we be expecting here?
Well, the software tool is free. You can go to Mouser.com and download that right now. It costs nothing. The boards, we kind of made them all roughly with a similar pricing strategy. Typical demo boards are about $200 a piece, anywhere from $200 to $300, depending on their size and complexity. These are basically in the $25 ballpark for a single rail, $50 for 2 rails. Some of the smaller interconnect boards are $15 or $35. The large breakout boards and integration boards are, I think, $75. So conceivably, this could, a large system might cost you $200 to $300, which is just about the same as you pay for a single demo board.
Right.
We price them aggressively like that because what we want to do was to enable people to test a large array of power and include that in their design.
Mm-hmm.
And that's worth it to us to have people experimenting with power and using and, grabbing that power attached for their signal chains.
The idea is also that it's reusable in a way that maybe a traditional demo board isn't, because now you have that much flexibility in your modular platform that you can break it apart and put it back together again in a different configuration later.
Yes, absolutely.
Awesome.
You can take these. As a matter of fact, it was one of the design requirements. We actually oversized the resistors that were most likely to be changed, such as the frequency setting resistors and the feedback resistors and some compensation components. Those were left intentionally in 0805 size resistors when they could have been made 0402 just to ease and facilitate changing those parts out frequently.
Well, I got to ask, I assume that in the design process, as you guys were putting this system together, that you guys got to do some testing in-house. Did you guys sit down and kind of I'm picturing a room full of engineers just kind of playing How did you get to test some of these things, and was there like a little bit of joy in your mind getting to build something from scratch?
When we first released the SAP program, it was done internally, and we shopped it around to various groups that were responsible in the precision technology group. And all of the engineers who used it, they loved it. They thought, this is awesome, because they didn't have to wait for custom demo boards from the Power Applications group. This was something they could tackle themselves. So we kind of field tested it inside the company before the decision to release it was made. Absolutely.
Yeah, maybe the lucky few guinea pigs.
Actually, I presented this at our general technical conference in 2019, and my display was one of our new, very high-end analog to digital converters, and it was being powered off one of these SCP board arrays. And I had a little switch. You could switch back and forth between the power that was already on the board or taking it from this SAP board, and you could see the difference live between the two different power approaches in the FFTs as it was running.
That's pretty slick, James. All right, so we do have a really cool portion of this tech chat is going to be you leading us through an example here, showing us how to use the SCP configurator, right? So can we help people if they want to follow along at home? Can we just help them set up their desktop a little bit if they want to pause, go tool around, maybe download some stuff, and then come back?
Sure. So let's see. I guess we should start with where you can find these SCP resources. There's scponmauser.com, the signal chain power hardware evaluation platform microsite. You can get the configurator tool there. If you run into any problems, there's an SCP forum on Engineer Zone on the analog.com domain. If that still doesn't answer any questions, there's always central applications.
Perfect.
So the SCP configurator software tool, we like to say datasheet numbers in, system design out. It was developed for people with no prior power design experience. We have a simplified interface. That is, you put in the input voltage range, choose the number of rails, and then choose the output voltages and currents and whether or not you want a low noise option. It's not quantitative. It's just, yeah, I want low noise if you think you might need it. And it has a complete power solution output. With that is a board design and PDF report file, as well as links to the SAP platform for easy ordering. So it's kind of a 1, 2, 3 process. It's designed intentionally to be very simple. So you start by downloading it and installing it. It's a fairly straightforward process. So once you've opened up the software configurator tool, the first step from the drop-down menu is to choose the number of rails you need. The software is designed to allow up to 5 rails. We found that to be the most common. Let's say 2 rails for your amplifier, 2 rails for your ADC, and perhaps a 5th rail for your logic voltage translation. So once you've chosen the number of rails, you simply have to fill in the input voltage range and then type in a number that corresponds to the output voltage and expected maximum current and whether you need low noise for each of those rails, and then click Generate Solution. It's that simple. Once you've clicked Generate Solution, it crunches some numbers and it figures out the best parts in the portfolio to use, as well as the best topology to use, and it displays a graphic of how that system array will look, and it presents it in the screen. It also generates a board list that's there on the right-hand side. Those are some alternate parts in case the chosen parts either aren't available or they don't work quite like you expect them to. So you can always order some alternate parts at the time you order the parts it suggests is the best parts to use. The next step would be to click Generate PDF Copy. When you click that button, a small pop-up box will appear. You'll type in whatever you want to call the file name and click Save. As an alternate option to account for some flexibility that a system designer might require, we've also allowed the option to choose a number of dual output boards. You can select up to 2, since 2 dual rails would create 4 of the 5 boards. There wouldn't be room for any. So you can choose 1 or 2 or none dual output boards from the drop-down menu. Once you've chosen, let's say, 1 dual output board, as we're showing here, a new window will pop up. It combines the first 2 rails as a dual board, and the one rail is always going to be positive and the other rail is always going to be inverting. That's an SCP standard. So you type in same thing, the positive and negative voltages and currents, positive and negative, or I should say negative voltages and currents, and again, whether you need low noise from that, and just click generate solution again. Once you've clicked generate solution, as you can see, it simply replaced the two single switcher boards that were there before with a single dual board. And in some instances, perhaps for a solution size, making it more compact, a person might want to choose a dual board. And again, you can save that to a PDF for your new design. Once you've saved your PDF report, if you open it up, you'll see that it gives you some documentation that you can use either to take out in the lab and modify the board or to present to your engineering manager for a plan or approach that you want to take for system development. The PDF has links that takes you to the individual boards where you can download more collateral. It also serves as a pictorial guide for how to assemble the boards when you receive them. Once you have your PDF report and get the collateral, you can use that to actually help you modify the boards. Because the solution report contains the links to those demo manuals, shown here is an example. The software has generated what to set those voltages to, and you can then open up the demo manual, and there are tables there that help you choose the right resistors to set those voltages as well as some other components. So you verify the feedback values, configure them, plug the boards together as shown in that PDF report, power them on, verify the system rails with some kind of a meter. And, if you run into problems, you can always contact us in that PDF report. There's a contact us button, and that'll take you to the engineer zone where you can get help if you need it.
All right, it's an awesome walkthrough. It's a really simple process when you break it down that way.
That was by intentional design.
Nicely done. All right, so people are going to walk away from this with the idea of, the why behind it, why you guys decided to design this platform, with an idea of where to go to get started, and now a nice handy little tutorial of how you can start working with your first design. So let's wrap up with just a couple of final thoughts, shall we?
Yeah, sure. So in summary, what we've covered here today are the kind of the two halves or two pillars of the SCP program. There's the signal chain power hardware evaluation platform. With that, you can build complete power systems for low power signal chains, and you can quickly reconfigure those combinations to test them for their performance. There's also the SCP Configurator companion software tool, and with that you can generate complete solutions for target signal chains from the power specs of the data sheets of those parts that you're using, as well as create a design document with interactive links to the hardware web page. And you can always get those from Mauser.com as well.
All right, and before we let you go here, James, let me just ask, for thinking about this whole exercise has been putting yourself in the shoes of an engineer who needs to design one of these systems and kind of anticipating what they're going to need and trying to get a better understanding of what the system design process really looks like so you can give them better tools for it. How about, do you have any fun, cool, interesting applications that you can share with us about how you've seen this be used already? I mean, you don't have to name drop anybody if you don't want to, but can you tell us about maybe a really cool example of a use case that might really resonate with anyone out there listening?
Yeah, so most of these are meant for, I should say, the prototypical signal chain that has an amplifier, some kind of a filter, and some kind of an ADC. There have been several that we've done for demo boards that have recently been released from Analog. Some of our high performance SAR ADC demo boards, the power that is on board those demo boards was actually tested and developed using the SCP boards in the lab while they were being developed. The parts that are on those boards were chosen specifically because we had the collateral and the layout already done, so they were able to quickly migrate. So all the claims I'm making are not just hypothetical, they've actually been done. And if you order some of our newer SAR boards that are full-fledged demo boards from Analog, it's been tested and proven using the SCP project as proof of concept. So there have also been a couple high current op amps that they were able to use some of the higher current bucks configured both as a positive and inverting buck to deliver enough current for those. Those were for a customer, obviously, so I can't name names, but they have been used out in the industry already, and they've been used to great effect.
Kind of engineer tested, Analog Devices approved, huh?
Absolutely.
Awesome. Well, we've had a lot of conversation throughout this process, kind of understanding what the needs are, what the pain points are for those engineers designing these signal chain systems. The blood, sweat, and tears that kind of went in the background from the Analog Devices engineers like James, who basically thought about what would be really cool, what would have been really helpful if they'd had their druthers designing in the past. And then, this more or less hyper simplified tool again that, I don't know, James, maybe you'd really wish that you had one of those in the past.
So, it's interesting that you mentioned that, because one of the last really high performance signal chains that I did in my days as an applications engineer was shown on slide 5, I believe. There's a picture there. It says giant copper clad.
This is yours.
And I spent the better part of a day and a half out in the lab modifying those demo boards, putting whiteout underneath their little standoff, little plastic feet standoffs, and putting them down. So when I lifted them off, I had a place to drill a hole to then screw them all together onto that back plane. I then wired them all up, wired them together. I had to scratch out little bits of copper to make some additional connections and take those boards and modify them. That is shown side by side with the equivalent SCP hardware. You can see it's a lot smaller. Those did not plug together. I had to wire them together. It involves soldering, drilling, and some cursing.
Yeah.
but that's shown side by side with in actual scale what the difference between those demo boards and the SCP boards would look like.
So what we're seeing is a visual representation of those blood, sweat, and tears that came directly from you.
This was born out of frustration with the way everyone's currently been doing it. Exactly.
Well, it's difficult to come by a better vote of confidence. I guess came from actual frustrations of an actual design.
This was not an example of a solution looking for a problem. This was a solution to a particular problem, and one that we had done over and over and over again till we stopped and said, "There's got to be a better way."
That's fantastic. I hope you guys put that on the box. Well, I think we're at our time, but James, thank you so much for all of the time and the insights, and for sharing your personal traumas designing and creating a tool like this one so that other people can not have to do what you have done in the past.
It's a rough job. A lot of people do it, but I guess you could say the folks at Analog and Mouser just look good doing it.
Yep. Not the hero we deserve. All right. Well, thank you so much, James. It's been a pleasure.
Well, thanks for your time, Kate.